Okay, we're going to start here by defining what we mean by the work of a force. And essentially, by definition, the work of a force is that force times its displacement in the direction of the force. So if my particle is following this path here and I place a force on it, again, what I'm really only concerned about is the force in the direction of motion, in the direction of the displacement. So that's essentially a cosine of this angle, right, to get that force in the direction of motion. Okay, so it's force times ds cosine of the angle, which by definition is a dot product. So I can find the work simply as the force dotted with displacement. Okay, putting this in terms of integrals as opposed to an infinitesimal change in work, the total work between two states is essentially the integral of f dot displacement, force dot displacement. Or another way to think about it is the force times the cosine of the angle between the force and the displacement times the displacement ds. Okay. So some of the properties of this is that we actually get a scalar. That is, you don't have work in a specific direction. Okay, you just have positive or negative work. Okay, and it's positive if the force does positive work if the force is in the same direction as the displacement. Okay, and force does negative work if it's in the opposite direction of the displacement. Okay, and the units of work are simply force times distance, which is a foot-pound, or a Newton meter, which we call a joule. Okay, so again, force through a distance in the direction of the displacement that occurs. Now, common situations we got here, if we've got just a straight line, a constant force, basically my integral falls away, right? So theta is constant, the force is constant. So it's just that force, again, in the direction of the displacement times the displacement, S2 minus S1. Okay, so if I got a constant force, straight line, I can just write it without the integral like that. Now weight, okay, weight, the work due to gravity essentially is what I'm dealing here with, okay. So as I have it drawn here, my weight is in the negative j direction. It's downward in the negative y direction. And I'm going to dot that with my displacement going from S1 to S2, which is basically the change in the x direction, change in the y direction, change in the z direction. But when I take the dot product, all I really care about is the change in the y direction, right? Dot product will just be mg times dy, okay? Well, gravity, mass is constant. That comes outside of my integral. And essentially all I'm left with is that the work due to the weight is simply mg times the change in distance. Now this negative sign says, okay, it's a negative work because if I move up, if delta y is positive, I'm doing negative work because my gravity is acting downward. Okay, so the work is in the opposite direction of a positive displacement. That's why I have a negative value there. Again, it's probably just easier to recognize, okay, is force going with displacement or against displacement to determine if it's positive or negative. The last kind of force we want to talk about is a spring force. Okay, so again, it's just the integral of the f times ds, where my f here is ks. And again, I have a negative sign because, again, if I'm pushing on my particle, my spring force is acting against that. Okay, so again, I'm pushing on the particle, compressing my spring. That means the spring is actually pushing back. Okay, so the spring force is pushing against the displacement, right? Again, if I move to the left here, the force of the spring is pushing to the right. That's why I have the negative sign. Again, because my spring force opposes the compression. Okay. So with that, k is obviously a constant. I bring that out, and I'm just left with sds, which is s squared over 2. So again, I can have the work of a spring as just the difference in the 1/2 ks squared. Okay. So again, work of a force is simply force times displacement. And I have a few common situations right here. Remember that the sign is based on if the force is in the same direction as the displacement or not. Okay. Now, this leads us to its relationship with energy. Okay, so I'm going to start with just a force following along a path. So I've got a tangential direction, a normal direction. Okay, I'm going to start by you remember my kinematics. Okay, so I've got some velocity, so I've got some acceleration, all in the tangential direction. I've got a displacement on the path. Okay, so there's my kinematic equation. Okay, Newton's second law tells us that the sum of the forces in that tangential direction equals the mass times the acceleration in the tangential direction. So rearranging my kinematic equation, I can just replace AT with V times dV ds. Okay, so again, I'm just summing the forces in the tangential direction and using a kinematic equation for acceleration in terms of velocity and position to do that. So now what I can do is basically integrate both sides, bring ds to this side and integrate. Okay, and I'm left with mdv over on the right side. M is constant, so I can bring that out. So I'm just left with the integral v dv here. Over on this side, this is my definition of work, right? It's a force times the displacement. So essentially, the work done on a particle is equivalent to the change in the 1/2 mv squares. And that's when I take the integral of v dv, I get v squared over 2. And what I have here, rearranging this equation, bringing 1/2 mv1 squared to this side, basically 1/2 mv squared is by definition my kinetic energy. So I can have an initial kinetic energy plus all of the work being done, okay, of all the forces, and that'll equal my final kinetic energy. And this is the principle of work and energy, right? So I have an initial kinetic energy. If I do work on that, I'm going to get some sort of final kinetic energy, where kinetic energy, again, is defined as 1/2 mv squared. Okay, now, taking it a little step further, the same holds true for a system of particles, right? So if I've got all these different particles bouncing off one another, I have a whole bunch of external, a whole bunch of internal forces. The bottom line is it's the same idea. It's just I have several kinetic energies. I have several 1/2 mv squares because I have several little m's in my particles. But it's still a scalar equation, so I can just add them all up and add them together. So all of the kinetic energies plus all of the work done on all of the particles equals all of the kinetic energies summed together. Okay, and it's just one equation, again, because it's a scalar equation. I don't have directions or anything like that. Of course, I do need to know how the force relates to the displacement so I can figure out the magnitude and direction, or positive or negative in the magnitude of the work being done. So again, key thing here is just remember that initial kinetic energy plus the work being done equals some final kinetic energy.